So it might be difficult to figure out the A and the B values. You could have a stab at the L value at least, because that's just how much brightness is in the image. So if we look here at, say, an RGB image, in the red channel and the green channel and the blue channel, they're quite different. And if you wanted a black and white version of this image, if you weren't prepared to settle for one of these, which each one is slightly distorted really, you'd have to take the red value of each pixel, the green value of each pixel, and the blue value of each pixel and average them to see how bright that pixel should be. With the LAB system, the L channel, the lightness channel, has that separated out. So in the LAB system, you have the lightness part of the pixels, the color, and then you have the A and the B, which provide you with sort of the color information. So if you have an image in the LAB format, it's trivial to extract from that a black and white version, because the lightness information is just all lined up there waiting for the plucking. So if this was like a byte for the lightness for each pixel, then a byte for the A, a byte for the B, then a byte for the lightness, a byte for the A, a byte for the B, a byte for the lightness, a byte for the A, a byte for the B. Well, you could just take all the lightness values and pile them up and ignore the A and the B values, and there you are. You'd have a perfectly good black and white version of the image. We don't use the LAB system that much. We're mostly interested in it for this property. You might have in the past worked with images in LAB form if you knew that the final delivery mechanism for the images was going to be analog television. So I think there was a Philips console many years ago, before PlayStations and stuff, called CDI, I think it was called. And I think, if I'm not mistaken, images for that had to be saved in this kind of a format. And this was the one used, or something like this was used for analog television. And that was for historical reasons, because in the past we had black and white televisions and a black and white television signal. When we figured out then that we could make color TVs, we needed to have a color TV signal. And one approach would have been to, well, have the black and white signal and leave the black and white people watching that with their black and white TVs. And then we'll have a color, we'll also transmit a color channel, and people with color TVs can watch that. But of course, then you would have been transmitting the same thing twice, which was a lot of effort in terms of resources. So engineers devised a scheme whereby you would continue to transmit the black and white television information, the black and white channel, and then you would supplement the black and white information with the information that was needed to calculate the color. So, I mean, I'm talking in very digital terms, but of course this was all analog. But in general, what you're saying, look, here's the black and white value. Now, in order to calculate the color value, you need these two other pieces of information. And so the people with black and white TVs could continue to just look at the black and white part of the signal, and then people with color TVs could take the black and white and this supplemental information to generate the color image together. And so that's the useful property of the LAB system that we're interested in. The lightness part of the image and the color part of the image are separated out nice and conveniently. The lightness part we call luminance, and the color information we call chrominance. And another important feature of that is that humans are much more sensitive to luminance than they are to chrominance. So we can do some jiggery pokery and save some space. So it turns out that subtle variations in luminance are very easily detected by humans. We're very sensitive to that. But subtle variations in color, we are less sensitive to. We don't mind so much. And JPEG, for example, does a trick whereby it separates out the luminance and the chrominance information, and it leaves the luminance information intact and then reduces the quality or reduces the amount of data in the chrominance part that's transmitted or that's stored. So it reduces the size of the color part of the information. And typically, we don't even notice. So I'm going to give you an extreme example here, where this is a picture of me, obviously, and this is stored at 24 bits per pixel. So each pixel requires 24 bits. The original image was 400 pixels by 400 pixels. So we're talking 480,000 bytes. What I did was I converted this image to LAB. So instead of it being, 8 bits for the red, 8 bits for green, and 8 bits for blue, there was 8 bits for the L, 8 bits for the A, and 8 bits for the B. I then took the luminance parts of that and shrunk them down so they were tiny, so that the quality of them was really, really poor. And then I reincorporated them back into the image just to see the consequences of that. So I can maybe show you how to do that in the Photoshop lab even if you wanted. So in this image here, the luminance channel is still preserved there, and it's 400 pixels by 400 pixels. But I reduced the color information to 1/16 of what it was before. So I threw away 15/16 of the color information. It's only 1/16 of it left, which is like way less than 10%. And the picture isn't actually that bad, joking aside, obviously. So this image here is about 1/3 of the size of this one. And you can't really see a huge, huge difference. I mean, if this one was costing $4.80 to send if you were roaming, this one here would only cost $1.60. This one is clearly very good value. It's about 1/3 of the cost. And that's because basically humans suck at color. We're not very sensitive to subtleties of color, the subtleties of luminance, to the same extent that we are, the subtleties of chrominance to the same extent that we are with luminance. Can anybody see where it starts to go? Anybody spot the difference? The tie. I don't see a difference in the tie, but that's where I would expect to see a difference. I don't see it myself, but that's where I'd expect to see a difference. I think we'd have to zoom in on the tie to see it. Can anybody see anywhere else? Yeah, the red splats there from the Space Invaders on the wall. The colour there starts to give a bit. If you zoom in there, you can see sort of bluey stuff there starts to emerge. And that's because the colour information for that part of the image isn't very precise. Now that you see it, now that you know it's there, it's easier to see it. Also, this image isn't all that colourful. I mean, if this was, Carnival in Rio de Janeiro or something, you'd probably see it more. Generally, where there are boundaries where one colour stops and one colour starts, you might see some overflow or some blurring of the colour information. But I think we can agree that as long as you keep the luminance intact, you can get away with a lot. By contrast, I have subsampled the luminance information to the same degree here. I did exactly what I did with the chrominance to the luminance. And you can see that we're really sensitive to that. And this was only one channel. The luminance is one channel. The chrominance was 2 channels. So this is still about 2/3 of the size of the original. Whereas the one I showed you was about 1/3. This is still about 2/3. But it's all chrominance information, and it was the luminance information that I screwed up. And you can see that's a whole different ballgame. So that's one technique we can use to reduce the amount of data that it takes to store an image. We separate the luminance and the chrominance, and then we flat the chrominance basically. And we typically get away with it. Okay? So that's the LAB system. You won't generally see the LAB system that much. It's not used that much because it was mainly used when your target was analog television, and there's no one doing that kind of stuff anymore. But it is useful from this point of view. You can separate out the luminance, the chrominance, and we can see it at work. No. So if you are specifying color for a web page or for digital television, say, you use RGB values. So if we were to get the CIT style guide, it says to you there that the CIT red, which I think is very close to pink actually, that CIT red has this RGB value. The red is this, the green is this, the blue is this. And so if you're making a presentation or a video, or you've got, super cool graphics or something on the screen, you can make them that RGB value, and that fits in then with, the CIT corporate identity. However, for brochures and posters, for printed materials, it specifies the CMYK value. So CMYK is the color system that we use in printing. And that's the 4th color system we're going to look at. So it's C for cyan, M for magenta, Y for yellow, and K for black. Because I guess B could have been confused with the blue ink. CMYK is subtractive. So the more you add, the darker it gets. So with RGB, the higher the values, the more light you shine, the brighter it gets. With CMYK, the higher the values, the more you add, the darker it gets. Your starting point is a white sheet of paper. The more you put on that, the darker it's going to get. It's quite intuitive because it's like when we mixed paints at school. So if you mix blue with yellow, you get green. If you've we usually express them as a percentage. So you go from 0% cyan to 100% cyan, for example. If you've no cyan, no yellow, no magenta, no black, if you've nothing, if you've got your white sheet of paper with no ink, you're looking at white. If you've no cyan, no yellow, no magenta, and 100% black, you've got black. I think it may be possible in a mathematically ideal world that if you just had the cyan and the magenta and the yellow together at 100%, that you'd get black. But we don't do it that way. We have the 4th color because black ink is cheap and we use a lot of it. I have a printer at home which has 6 colors and black. That was supposed to be better, but whatever. No. So that's the cyan, magenta, yellow, and black. If we look there at the top left, if you have 100% cyan, go figure, it's all cyan. You've nothing else. If you've no cyan, 100% magenta, 0% yellow, 0% black, then obviously you're going to get magenta. Looking there at the top right, we've got cyan is 36%, we've 0% magenta, 42% yellow, and 46% black. And that gives us a shade of green there. I would have expected that to be a bit darker. with the 46% black, but there we go. Bottom left there, we have no cyan, no magenta, no yellow. We just have black ink. And at 54% black ink, it's that shade of gray. We here, that red one there, we've no cyan. We've 83% magenta, 81% yellow, and 7% black. I would have expected that to be a bit more orangey, actually. There we go. And so on. Just as we saw with the RGB system, you can, in things like PowerPoint, you can modify the color, and you can see the color system at work. So here we have CMYK sliders. And you see that if we turn up the cyan, we get stronger, darker blue. Here I'm cranking up the magenta. It's getting darker. If I want to make orange, I would have very little blue, and I would have lots of red and yellow. A bit more or less red, more yellow. If I wanted to make a shade of green, I would get blue and yellow. So I'll turn down the yellow there. I'll turn down the magenta. I'll turn up the blue. And I'll start adding some yellow. And we should start to see it get green. It's not as green as I would have liked. Maybe we've got too much blue in there. Okay, so at 64% green, 64% cyan, 0% magenta, 63% yellow, 0% black with that shade of green. I think I'd like a bit more yellowy, so I'll crank up the yellow a bit more. Trying to get a bit greener. Let me turn that down a bit. And there are even equations you can use to convert between RGB and CMYK and things like that. So the best way to get to grips with these color systems is to just go into something like PowerPoint and mess around with the color sliders. So here in this one, we've got RGB, CMYK, and HSB. Now, it turns out that there are people for whom specifying color very precisely is very important. One of the issues we have with color technology is calibration. So if you look at something on my screen here and we look at your screen here, they may not be the exact same shade of yellow. Perhaps my screen is very yellowy. So if I had a photograph on my page, if I had a photograph on my screen, I might find that it's very yellowy. So I might reduce the yellowness of it, and crank up the other colors. But then if I sent that image to you and you looked at it on your screen and your screen was perfectly normal, I would have overcompensated for the yellowness of my screen, and you'd see something that I hadn't intended. So if you're working in the color business, if you're a graphic designer or a fashion designer or working in television, whatever, you need to calibrate your screen so that it's at some standard that everyone has agreed on. So you can even get things that clamp onto your screen and we'll adjust it so that everything's perfect. I mentioned that for screens it's RGB and for printing it's CMYK. And for some people it's very important to have exact color. So this company here, AGT7, I don't exactly know what they make, but they had an ad campaign in a graphic design magazine where they were saying, sometimes, for some people, red isn't enough. We need to be precise. And I thought this was quite clever because, of course, the people reading this magazine would have been aware that C0, M0, Y0, and K100 is, pure black. They had another one here, which I liked. So cyan 0, magenta 60, yellow 90, black 0 is obviously orange. And then one more. So not just color, exact color. It turns out that in fashion and interior design and stuff, there's actually a whole other system again. So if I was a designer for Zara, and I was on my holidays up in the mountains in Italy, and I saw a wall that was, a gorgeous shade of orange, I might say, oh my God, that orange is the new black. I must have it, Rather than taking a picture, that person would probably whip out of his or her pocket a little yoke, maybe the size of a USB stick or something, that you could actually hold it up to an object and it would examine it and it'll read it and it'll tell you this is, RGB whatever, CMYK whatever. It would also actually tell you that it was something like Pantone Orange 90 or something like that. So Pantone is a company that is in the color specification business. So let's say Zara is making a dress and the bottom half is made in Morocco and the top half is made in Portugal, and then they bring them back to Spain and stitch the top and bottom together to make the dress. Well, they don't phone up the factory in Morocco and say, we want this orange, and then phone up the Portuguese factory and say, and we want the top in orange as well. It's like when they come back, they'd better match, Orange, there's a lot of range in orange. Black is not so bad because black is black kind of and white is white. But orange, what's that? So they wouldn't use the RGB values. They might at a pinch use the CMYK values because dyes mix the same way, paint mix. But they would probably say, no, we're doing a load of stuff this year in Pantone Orange 90. And so the factory in Morocco would look up, this is how we make Pantone Orange 90. We mix this and this and this and this together. And when the stuff comes off the production line, someone would examine it. They would have a Pantone swatch, that would have Pantone Orange 90 on it, and they would have a look and see that it's a good match, and their quality assurance would check that. And so in some industries, you'd use the Pantone system. But for many people, specifying color very precisely is very important. We're mostly interested in the RGB system because that's how computer systems store images digitally. So in your mobile phone, your camera, it's the RGB system that's at work there. Okay. Any questions on that? Okay, good stuff. So guys, we'll look at some more things the next day.